So welcome everyone to this Green Bank Observatory Community Zoom. I'm Tony Ramajan. I'm the interim director here in Green Bank. And I'm just going to give you a couple of quick updates on the status of operations and maintenance updates here on the Green Bank Telescope. So I want to share with you, because if you have been calling into these Zoom meetings over the last several months, you've been hearing about we're repainting the telescope top to bottom. And so here's the first real pictures of the top structure of the telescope. This is actually at the very apex of the telescope, the large red light there. And you can see what used to be white is now completely sandblasted, and we're getting ready for paint. So, you can see the upper feed arm now all the down to the raw steel. And we are actually now coming to fruition here about painting the Green Bank telescope. So this is a great progress has been made over the last couple of weeks. And so we're very excited about, showing that off and showing that the progress makes on the Green Bank telescope. And this is all for the service of the community. We want to keep the GBT up and running for at least next 25 years. So we're giving it a fresh coat of paint. And so we could accept and work on the proposals that you are going to submit. So last week we sent out our call for proposals. It was on the 25th of June with a deadline of the 30th of July at 5 p.m. Eastern time. Remember, it's 5 p.m. Eastern time, not 5 UT. So make sure that you get those GBT proposals in. Just a couple caveats here for GBT proposals. We're not accepting any large proposals this semester. So we only currently accept large proposals in the A semester. So no large proposals here, in the B semester. So no large proposals will be accepted in the A semester. And we're also not quite ready to have the ultra wideband receiver yet for an actual proposal call. So just keep that in mind, that there's not going to be any proposal that's accepted that is requesting the ultra wideband receiver. So just keep that in mind when you're preparing your proposals. And as always, scientific staff here like Larry, who'll be introducing our speaker here in a minute, are here to answer your questions and help you through the proposal preparation process. So please reach out to the Green Bank staff through the help desk and when you are looking to prepare your proposals. So with that, I am going to hand it off to Larry to introduce our speaker today, and welcome everyone, and welcome Pamela to the Green Bank Community Zoom.
Thanks, Tony. So I'm Larry Morgan, staff scientist at Green Bank, for those of you who don't know me. And I'm here purely to introduce Pamela Freeman, who has just finished up her thesis with Renee Plume at Calgary. And apparently this is brand new news, but she's on her way to UNAM in Mexico to start a postdoc. So congratulations, Pamela. And Pamela's going to be talking to us about chemical diversity in high mass star forming regions. The way this Zoom is set up is that most attendees will not be able to unmute themselves. So if you have any questions, please put them in the Q&A, and I will read them out at the end of the talk. So with that, please take it away, Pamela.
Thank you for the introduction, Larry, and thank you so much for having me. Happy to share a little bit about my PhD research, what I've done over the past few years. Can everyone see my screen okay?
Yep, I can.
Perfect. So over the past several years in Calgary, I have worked and lived on the traditional territories of the people of Treaty 7, which include the Blackfoot Confederacy, the Tsuut'ina First Nation, and the Stoney Nakoda. And the city of Calgary is also home to the Métis Nation of Alberta Districts 5 and 6. So I do just like to place myself at the beginning of a presentation to acknowledge the land that I call home and its history, and to appreciate that I am just one of many people over many generations who have lived and learned here. And with that, I would like to get started with my talk about chemical diversity in high mass star forming regions, the work that I've done with my supervisor, Dr. Renee Plume, as well as our collaborators, Emmanuel Coe, Sandra Bottinelli, Bazawati Mukherjee, and Chris Monahan. And so just to place ourselves in the interstellar medium, the regions that I'm going to be focusing on in this talk, we have these collapsing clouds of gas and dust that are forming new stars. The molecular clouds collapse, form protostars. These have accretion disks, which eventually become planetary systems. And typically their stages are identified by continuum observations. But if we zoom in into one of those particular regions in protostellar cores, which have the core at the center here with an envelope and usually outflows, we also have molecular species formed in the gas phase and in grain surface reactions. And these molecular species can also be pretty good indicators of what is happening in a protostellar region. And this is a very incomplete overview of the mechanisms that can go on here. And so typically 2 distinct regions have been pulled out from those chemical molecular studies. We have hot cores on the left and warm carbon chain chemistry sources on the right. So hot cores have abundant complex organic molecules with a compact and dense hot, which is typically meaning over 100 degrees Kelvin, central region. Those molecules could be like formaldehyde as a precursor, methanol, or dimethyl ether. The warm carbon chain chemistry sources have abundant carbon chain molecules in the about 30 Kelvin, which I talk about as warm, extended envelope. And those can be a precursor from methane, forming something like propyne. And how these 2 types of sources could become a dichotomy is how carbon acts earlier in the star forming process. So in the top row here, I have if carbon is taken up in carbon monoxide, we will have that depleting onto the grain surfaces early in the star forming process. On the grain surfaces, there will be reactions, mainly hydrogenation, to make larger molecules. As the protostar warms up, those molecules will then evaporate back into the gas phase, and we will get a hot core source. But if carbon remains in its atomic form, that will deplete onto the grain surface. It will create larger molecules, namely methane, that will evaporate back into the gas phase as the protostar warms up. The gas phase chemistry can create longer carbon chains, and we'll get a warm carbon chain chemistry source. But this might not be as strict of a dichotomy. There have been shown sources that are showing signs of both hot core chemistry on the smaller scales, small spatial scales, and warm carbon chain chemistry sources on the larger, more extended scales. So more recent studies have kind of shown that the chemical processes in these star forming regions are more complex than we thought. And so my PhD project aimed to address some of these open questions of carbon chain chemistry and carbon chain sources. Is it prominent in some or all high mass star forming regions? What are the physical conditions that they exist in? And how do they compare to complex organic molecules? And so towards Cygnus X, we matched 3 high mass star forming regions with the Green Bank telescope and the IRAM 30-meter telescope in a wideband spectral survey. And just for the sake of time for this talk, I'll be talking about 2 of those sources. And I want to just talk a little bit about our GBT observations, since this is a GBT talk. We did DAISY on-the-fly mapping with the Argus instrument. So we scanned over our sources to create a map, but in this DAISY petal pattern, which actually was very effective for getting a good view of what these sources look like. And I would like to thank Larry Morgan, who's here today, and David Freyer for help with those GBT observations. And so the 2 sources I'm going to talk about today, the first one is DR21OH, which is a young and clustered source in Cygnus X, which has several dense clumps within it. Our other source is IRAS 2126, which is a relatively simple, older system in comparison. It's an isolated dense clump in Cygnus X that so far shows evidence of one protostellar system. Our third source, which I won't talk about today, is AFGL 2591, which is massive with one dominant protostellar source. So within our data cubes, this is combining the GBT and the IRAM data, we do find several lines of the complex organic molecule methanol, as well as its precursor formaldehyde, and the carbon chain molecules propyne and cyclopropionylidene. And these are molecules that I would like to focus on today. These are the ones we have analyzed because we did find several lines of each of them. And so for the analysis, with our collaborator Sandrine Bottinelli, she developed a local thermodynamic equilibrium model that is in Python, but based on the formalism of the Cassis software. So we were able to take this model and loop it over all pixels in our map to create parameter maps showing the physical environment of a region. So this is just an example map of one transition of propine. And this is what we'd be able to pull from that model, collecting the physical components that would recreate this spectra. If you would like to look into the code, this talk is partially an advertisement for it because it's very useful for looking at wideband mapped observations. The code is here. So first, talking about the IRAS 2126 LTE model results. This was published in a paper in 2023. You can find it, the QR code in the bottom corner here. The picture I'm showing here is showing the two carbon chain molecules in the left columns and the complex organics in the right column. And then the different parameters are each row. Column density on the top, excitation temperature, velocity, and line width. So there are just a couple things that I'd like to point out of all of these graphs. First, we can see that the carbon chains and the complex organics have slightly different distributions. The carbon chains are more extended, but the complex organics are more compact around the protocellular source, which is marked by an X. The complex organics are also at a slightly warmer temperature than the carbon chain molecules. We don't necessarily see hot core temperatures above 100 Kelvin, but we assume that's because with our single dish observations, we are smoothing out the hot core and we don't necessarily have the resolution to get in that close to the protocellular source and see that region. We're smoothing it out. The notable part about the velocity here is that the velocity gradient is different between the carbon chains and the complex organics. So we have a north to south gradient in the carbon chains from red shifted to blue shifted, aside from the velocity of our source. And it is slightly offset for both of the complex organics. So that is notable just to see that we are tracing different things with our carbon chains and our complex organics. We're assuming that the carbon chains come from the extended envelope from a larger scale outflow, and the complex organics are coming from a more compact region and looking at a smaller scale outflow. So if I pull that to a little graphic, compared to the previous pictures, I'm not a data visualization artist, so please bear with me here. But this is just a little picture showing what we expect to see of IRAS 2126, what this is showing us about the source. There's a young early type protostar deeply embedded in a hot core. There is a central dense region of molecular gas, which is oriented perpendicular to a small scale outflow. And this gas is interpreted as the envelope and potentially a disk in here. The small scale outflow is traced by small molecules and corresponds to the one that we see in complex organics. And the large scale outflow is oriented south to north, traced by carbon monoxide, which we see in our carbon chain molecules. So moving on to our second source for DR21OH. As mentioned before, this is a younger and more clustered source. So our integrated intensity maps look a little bit messier than what we would see for IRAS. These results were published in a paper just last month. The QR code is here if you'd like to go find that. So here I'm showing integrated intensity maps for propine on the left, formaldehyde in the center, and methanol on the right. And each of these plots is just a different transition line from each of those molecules. And the stars in here represent sources that have been found previously to be potential star-forming sources, with the main one, DR21H, marked by the black dot. So just from a first glance, we can see that each of these transition lines is showing us something different within the source. The cold gas maybe compared to the hot central region around DR21OH. So to zoom in on that central source, we have split it off from the rest of the complete region that we have mapped. And we separated the other sources into different LTE models. This was mainly because what we were seeing in these spectra which I can show after if anyone's interested, or you can find in the paper, was that they had different line profiles. And so it wasn't easy to model the same components across the entire mapped region. So I'm just going to talk about the small box around DR21OH for this talk. So this plot now shows all of those physical components that we were able to pull from the LT model, that we were able to discern from our spectra. In the top row, we have 5 different physical components of methanol. In the bottom row, the first 3 are the 3 components for formaldehyde, and then the last 2 are the 2 components that we found in propyne. They've been lined up in column based on similarities that we found between these molecules. So in methanol and in formaldehyde, for the first 2 components, we found them associated both spatially and in their velocities, that they could be associated with the cores of MM1 and MM2. So these are just 2 clumps within the DR21OH source themselves that within them show signs of further fragmentation. The next source we found was shifted in relation to the velocities that we knew for these sources. It was also offset compared to the clumps MM1 and MM2 marked by the 2 X's here. We associate it with a molecular outflow in the complex organic molecules and its precursor. And then in our last 2 sources, they were more extended, cooler, but with similar velocities to what we would expect for MM1 and MM2. So we associate them for both methanol and for propyne, the larger extended envelopes of MM1 and MM2. And so overall, just looking at what we would expect and incorporating what we had for the other sources within our full map, we have these 2 dusty condensations, MM1, MM2, embedded in a massive protostellar source, which have further cores embedded within them. Within these, they have shown signs of maser and molecular outflows. What we found for methanol and formaldehyde corresponded to those molecular outflows. The maser outflows were shown in different velocities and towards different directions from this source. They would be the blue and the reds here, but what we found was this blue striped outflow. There's an extended ridge that has cooler temperatures with denser regions along the filaments. And we have these denser clumps denoted by these N sources along those filaments. But just because we can find these correlations between what we see from the physical parameters that we have obtained from our models to what we know about the source from the literature, or what we can interpret these physical parameters such as density and temperature showing us, we turn to a chemical evolution model in order to determine what the most likely formation routes were for these molecules. So the novelist Gasquet code allowed us to determine those formation routes. And the plot I'm showing on the right here just shows the first step of one of our models for formaldehyde and for propyne, where we looked at a warm-up model. The cloud was allowed to evolve in a cold phase for several years before warming up just because the protostellar started to heat up the region. And so for both formaldehyde and for propyne, these models, which are shown in the colors in green and in red, did match to our observed abundances. And the 3 different lines for each one is just showing those different physical components, and 2 for propyne. So we do see it appear in the gas phase as the protostar warms up the cloud to temperatures of 20 to 30 degrees Kelvin. And so for propyne, there is one caveat to this model. It only appeared in the warm-up stage if the extinction was really low. So for example, if it was at the edge of a cloud, not deeply embedded within it. And we also found that it was mainly due to grain surface formation, which is unlike the worm carbon chain chemistry mechanism that I introduced earlier. So that is, a notable finding from this model. What we weren't able to do with methanol, it's a little more complicated molecule, is we were unable to reproduce this at the densities and temperatures found for the protocellular worm-up stage. So we have to look into other models that might explain why methanol could be formed. For example, we could look into a shock model where some other mechanism will liberate the methanol off of the grain surface into the gas phase. And so I'd just like to talk a little bit about the next steps, what we could do with this research and what we are going to continue to do with my collaborators in a postdoc position. Is right now we're looking into what other molecular groups could tell us about these sources. Within our observations with the GBT, we also found a lot of sulfur-bearing species detected in all of our sources. So what environment produces their gas phase abundances? And then if we could move on to interferometric sources, we could look at the physical environment of those sources at core scales, try to discern what those hot cores look like, if they are hot cores. And aside from that, expanding these to more high mass regions would be really useful, just to see if what we see in these resources is common for a larger sample of high mass regions. And then how can we develop this LT modeling code or non-LT codes to better suit these large data sets with wideband and mapping information? There's a lot of information that's coming in here that we can obtain with, say, the Argus instrument and a mapping observation. How can we better deal with all that data coming in? So I will just leave here with this summary, and I'd be happy to try to answer any questions.
Great, thank you, Pamela. I have a few questions come in. Please continue to add any questions to the Q&A or any follow-up. I will read the questions. I apologize for any misinterpretation I may make in reading the questions out, but I'll start with this one I'm pretty confident I can manage. What were the frequency ranges of your observations? Did you do a complete survey or target specific lines?
Yes, that's a very good question. So what I showed for in these papers here, we had two ranges for the GBT, one around 85 gigahertz and one around 96 gigahertz. Those were both 1.25 gigahertz wide. And then we had one band from the IRAM observations. It was 8 gigahertz wide, centered at 291 gigahertz. And there were also IRAM observations at 135 gigahertz. But since that is at a much larger beam size, we didn't include it in this analysis. The reason why we chose those ranges is that with the IRAM and the GBT, the 290 and the 85 and 96 do provide similar beam sizes, but also within these ranges, there are several potential carbon chain species that we would observe, and coincidentally, some complex organics. So while it was like a wideband survey just to see what we could get in here, we did slightly target it towards the carbon chains.
Thank you. And did you find any nitrogen-bearing molecules?
Yes. So we have in here faint lines of some of the cyclopolynes, so HC3N, HC5N, Indir21OH, as well as we found CH3CN. So we might look at the nitrogen species a little bit on top of the sulfur-bearing species.
All right, thank you. Some two, I believe, related questions. The first one, why do you consider the data showing an outflow and not an orbit? This was back on your slide 17, I believe.
Yes, so I will try to see here if I have representative spectra in my backup slides. Bear with me one moment, please. I believe. So this is an example of the DR21OH spectra that we had right in the center of that mapped region. Might pull up the IRAS instead. So unfortunately, I don't think I have the picture of the outflow source, but what we found in our spectra was there was a very distinct, broad, one-sided component within this spectra. And given the velocities and the location it was at in comparison to what the literature had presented, the most likely interpretation was an outflow. We do want to look a little bit into if there are other species within our sources, such as like CS or SIO, that are known as good tracers of outflows, and see what information that they give us about this same region. And that would allow us to interpret it a little bit better, but just based off the line profiles, the velocities that we found, and what's previously been known about these sources, that was our interpretation.
All right, thank you. A related question, which I'm going to, I'll relay. Do you think the outflows are associated with disks of the various components that have concentric regions at various velocities in individual spiraling formations?
So
if it's possible to get some clarification on that question,
yeah,
that'd be good.
And there is a difference between, for that IRAS and DR21OH, since for, say, IRAS, we do have just this one isolated source that we are seeing so far. And the difference between the two outflows could just be, some interpretations are precession. Other people assume that there might be a second source in there that we haven't been able to resolve yet. But this small scale outflow, since it is especially located perpendicular to the dense gas that is interpreted as a disk or is known as a disk, we do expect that to be the jet coming up from the protostellar source. For DR21OH, it's a much more clustered source within MM1 and MM2. There are 9 further cores fragmented within that. And within them, there have been seen different outflows. The maser outflows are potentially coming from sources within MM2, I believe, and are tracers of that high mass star formation process. The molecular outflow that we're seeing, we do just see it one-sided. Haven't found the redshifted counterpart of it. And so I think the interpretation is still a little bit open as to what's actually powering that.
I think that may answer the next question, at least in part, answer the next question, which is from Alexander Lapinov. We observed 3 H2O maser flares in DR21OH in 2023, and none after that until the end of July 2025. Because what happened to the source in 2023?
Yeah.
It seems to me like it's such a dynamic environment.
Yeah.
It could be a number of things.
Yeah, that's really interesting. We didn't see any like correspondence to the maser outflow, so we kind of ignored that side of the region. That's really interesting to hear, though. And also, one caveat for the methanol observations as well is when we first started doing the spectral line modeling, there was one transition in the 85 gigahertz data, like the 84.5 gigahertz line, that was unable to be reproduced in LTE, and I think it's been known as a maser. So we did exclude that from our analysis here. But I wonder if that line could show us anything. I'll have to go look into those papers.
Yeah, and yeah, you should have these questions. You should be able to access these questions later.
Great.
Paul, I'm not sure how tightly I have to keep to time here. Should I keep reading questions? We have a few more still.
If you've got a couple more, we have a few more minutes, yes.
Okay, I'll continue then.
I'd say about 4 minutes.
Okay, I will continue for 4 minutes. So is your work directed primarily toward understanding astrochemistry or toward using astrochemistry to understand cloud evolution and star formation?
I think so far it has been to understand astrochemistry, so to understand the kind of chemical evolution of these regions and of, at first, like a little bit about what those, like the molecular abundances and distributions could tell us about the environments of these regions, but more so to see the astrochemistry side of it. So the diversity of what we're seeing, if certain chemical evolution routes are distinct from others, what is the diversity of what we could find here? I hope that answers it. In the long term, maybe one day I'll go into the more the evolution. I do appreciate the GPT programs also. If you're interested in more astrochemistry and kind of looking at other stages of these, the Gotham and glucose surveys, I think with Brett McGuire and Samantha Scabelli, respectively, look at cold cores and pre-stellar cores, and I'll really show the capability of molecular observations with the GPT and kind of look more into the stellar evolution, I believe.
Thank you. And are cyclic carbon molecules modified PAHs formed in these regions? Do you know?
Yes. So we only found one cyclic molecule in our line, in our data, and that is the cyclopropanolidine. We only did the analysis for that species in IRAS and AFGL, and overall it was actually quite weak, and so it didn't give us too much information on its own. We did not look into PAHs, but that could be something to follow up with.
Another question. Often the nitrogen species tend to trace colder regions. Did you compare with lower frequency maps where colder lines might be more dominant?
Yes. If I'm remembering correctly, there's one paper that shows, I might have to look into our paper. If I have the correct reference here. I do apologize, I might not be able to answer it off the top of my head right now. There is one interesting reference that we found that for N38 and N48, the two sources here, we actually found that doing their modeling, there was kind of a bridge in between the two that was that even though they had kind of distinct line profiles and models, we were able to find another component that kind of bridged the two. And that was also seen, I believe, in a colder N-bearing molecule. I apologize, I can't have the reference off the top of my head, but it is in there somewhere.
Either, but I would be surprised if there are not ammonia maps of the other one. But yeah, as I say, I can't think of a reference right now. And as Renee and I recently found that the ammonia does not always map that well to warmer regions. But
yeah, very interesting.
Okay, I think
if I could plug the paper there, can look it up there, or I can send an email after to whoever asks that question.
That was from Glenn Langston. So yeah, feel free to contact him
Mhm.
to discuss that further. I'd also be interested in that myself.
Okay. Mhm.
We
Make a
can
note of that.
discuss offline. I think I've exceeded the 4 minutes I was given, so I should wrap
Oh,
things.
oh yeah.
But thank you very much again for
Thank you for having me.
talk. And I'm going to have to cut it short, but thank you very much.
Yeah.
Thank you all
Take
for
care,
joining
everyone.
us, and please be sure to come back to us in 2 weeks, where we will have another one of these fascinating discussions. In this case, the next one is going to be about, and I'm trying to get to our webpage. Well, please visit our website, and you can go under our community science webinar link and be able to find out what's going on. Here we are. It is Erica Behrens from the University of Virginia speaking of probing the kinematics of multiple and single protostar systems in Perseus with N2H+. So thank you all, and we'll see you next time.